Okay, hi guys. As I said, okay, now here we have our second process, okay, and property of gas. Our second process, it is isochoric process, and this isochoric process, it is when we have suppose we have a gas, perfect gas. Okay, we're analyzing for perfect gases. So and it is in a container that cannot be compressible or expanded. Okay, so in this case it's like suppose we have a container here and we have a cylindrical vessel, or we have a vessel like this one, and inside there is a gas. Okay, there is the gas. This is the gas that we have, and suppose I keep the volume of this vessel. The volume of this vessel is constant. Okay, it is constant. It is closed. It is constant. So it means that there is no way to this container to expand or compress. Okay, whether you increase or decrease the pressure or the temperature inside of this container, it doesn't change. So this is what we mean by constant volume processes. Okay, so for constant volume processes, what is the relation, PVT relation in this case? As we know, we are using equation of constant gases. Okay, like equation for perfect gases. Okay, like this one, PV is equal to mRT. We know. Okay, so suppose it is the same. We will assume here that this is the same gas. Okay, only one monoatomic gas. Okay, the same gas. It can be monoatomic, diatomic, or triatomic, or polyatomic gas. Okay, this is a gas that is in a container, and this cannot change its shape. This container do not change its shape. This is what we mean by constant volume. So PV is equal to mRT. Now let us consider for two states. Okay, because a process, it is always made. Okay, it's only possible to get a process when we have a substance that has been considered in two or more states. Okay, suppose we have here a substance that it is in one state. Okay, let me see, this is P and this is V. This point here, it shows that this is one state of the substance. Why is it one state? Because here I have one volume, one pressure, and one temperature. Okay, this is a state. Okay, this is the unique condition of a certain substance. This is a state. Okay, at this point. But if I have the same substance, okay, that having different condition, okay, different condition at a different time, so I have a process from here to here. I can say like this one, this is a process. Okay, because here I have more than one state. This is state 1, this is state 2. Here it will have different volume, different pressure, and maybe different temperature. Okay, it depends. Okay, so one state, second state. Okay, the travel that comes. Okay, because from here to here it takes a time. Okay, so this, okay, when I consider a substance changing states, okay, this changing state we will call process. Okay, and this changing state can be done, may be done by as a constant volume, as a constant temperature, as a constant blah blah blah, and so on. Nice. Now, okay, hope you got understand what is state. Now we will consider here for two states, one state or first state and second state. So P1, okay, and here we'll get V1 and then mRT1. For second state, P2, V2, mRT2. Is that okay? Yeah, we are together. See, now that we say that here the volume is constant, V1 is equal to V2, that is constant. Okay, this is constant. Here you know what is R. R is characteristic gas constant. Okay, so see, this is the same gas. It is only changing in state, so at different states. So this R and this R are the same, and this mass and this mass are the same. Okay, volume constant. Now what we have to find, as we did for the first case, okay, what we have to do, find V1 here and find V2 here. Okay, what is V1? V1 will be mRT1 upon P1. Here mRT2 upon P2. Okay, as V1 is equal to V2, what we have to do? So mRT1 upon P1 will be equal to mRT2 upon P2. So m are the same. What we will add, what will be the relation between them? So the relation will be T1 upon P1 is equal to T2 upon P2. You see, here I can say that if the temperature increase, the pressure will also increase. So this is, okay, the PVT relation in isochoric process. Nice, done. Secondly, we are going to find what will be the work done for isochoric process. For isochoric process, what will it be? Isochoric process, work done for isochoric process, it will be okay, for isochoric process. So we have to draw always PV diagram. Just draw the PV diagram. Isochoric process, what do we mean by isochoric process? Isochoric process, it is the one that the volume is constant. So we will have this one and this one, same volume. Okay, same volume. This will be V1, this will be V2, okay, and they are here. Here V1 is equal to V2, okay? So, as V1 is equal to V2, so here I have a pressure, and here I have also a pressure. I will call this one P1, and here P2. But see guys, what is work done? Work done, it is always the area occupied by the, how can I say, the expansion, okay, of the volume. The expansion or the compression of volume. So I have work done. Work done is a function of volume. It means that if the volume increase and decrease, I will have work done. Okay? And there is something very important. When work done of a certain substance, if it is positive, it means that the work done is done by the system. Okay? And this is always whenever there is expansion. Okay? Whenever there is an expansion, what is expansion? Expansion is decreasing in volume. If the system is increasing, if the volume of the system is increasing, it means that the work done is done by the it means that if the volume is increasing, it means that the work done is done by the system, and this is a positive work done because there is expansion. Okay, there is expansion. But if the work done is negative, it means that there is compression. Okay, it means that the volume is decreasing, and when the volume is decreasing, so the work is done on the system. Okay, just like this. Then okay, I will explain this later on with much more basis. See, now from here, what we will have to do. Now that I know, here the pressure is changing, but the volume is not changing. In the work done, it is what? The changing volume. Okay, this is also always a function of volume. So if volume doesn't change, what do we have here? We will have, okay, let me just write down here. This will be change from P1 and P2. We can just write down P2, okay, minus P1, then dV, and V will be changing the V2 and V1. So here, even though the pressure is changing, but there is no change in volume, we will just apply if you feel like, just apply what this one. So V here is constant. So when V is constant, derivative of a constant is 0. So this should be 0 directly, but I will just follow all the steps and things will be okay. Okay, this will be what? This will be, okay, first you got this one. This will be P2 minus P1 time V, okay, time V. And this V is varying between V2 and V1. Now we know that V2 is equal to V1. Nice. So it will be the same. Work done will be P2 minus P1. Then it will be V2 minus V1. So we know that V2 is equal to V1. So it will be P2 minus P1. And here it will be V1 minus V1. Here it will be 0. So the work done in isochoric process is 0. Okay, 0. Okay. Now I was explaining something. Yeah. Now I will just say, because whenever there is work done, when work done is positive, it means that the gas is expanding. Okay, expanding. And we can say work done. This work is done, okay? Work is done by the system, okay? The system is doing work, okay? For work done, this guy is expanding, okay? And the system is doing work. But if the work done is negative, it means that there is a compression. This is compression. And this is work done on the system. Okay, this is just a quick review for this one. Suppose you have this one. Let me just say, okay, this is a cylinder. Suppose this is a piston, okay, and this is like this one. Whenever this guy is compressing, this is V1, this will be V2. See, when I compress this guy till here, and he just came in to be here, what will happen? See, in the compression, volume will reduce from higher to lower. This is compression. So work is done on the system. So if V1 is greater than V2, then we will have work done negative. So work done in the system when there is compression. Okay, done in the system. But if it is in the opposite way, if the piston is here and it is moving, okay, due to high temperature, it is moving up. It is moving up. So here, V1 will be this one, the beginning, and it will end in here. It will end, suppose, here. This will be V2. Here, V1 will be greater than V2, then it will be what? Here, let me go here in this side. Let me say this one is moving up, then is V2. So in here there is a expansion. Why? Because V1 is less and this guy is greater. This is expanding. In the expansion, work done will be positive. It means that the system itself is doing work. Okay? Yeah. So okay, just forget about this one. This will be helpful in the end, not now. Okay? Yeah. So all we have to grab here is work done for the isochoric process is 0. Okay, is 0. Nice. Let's go now. Now we are going to move. So what is internal energy? Internal energy for isochoric process. as I said last time, so internal energy for isochoric process, it is the same, okay? It is the same. Why? Because internal energy doesn't depend on the volume or on the pressure of the gas. It depends only on the temperature of the system. So it is always mCV delta T, okay? Just like this. Okay, then what will be our heat transfer? So heat transfer Q, what will be our heat transfer Q? So heat transfer, okay, this is 3, this is 4. Heat transfer, okay, let me call this one heat transfer. How to calculate heat transfer when the volume of a certain perfect gas is constant? So heat transfer, as we know, is equal to W plus delta U according to the first law of thermodynamics. Okay, so energy can neither be created or can neither be created or how can I say lost? Not lost. Sorry, destroyed. Okay, we cannot create or destroy energy. This energy can only be transferred or transformed in a different kind of energy, and this is the expression for this one. So heat transfer will be equal to the work done in the system and plus the change in internal energy. So here we know that the work done when volume is constant is 0. So it means that the whole heat transferred will be transformed into internal energy directly. Okay, so here for isochoric process, Q, that is heat transfer, is equal to mCV delta T because this one is 0. Okay, so that's the point. Okay, so what will be our change enthalpy? Change in enthalpy, which as we know here, change in enthalpy will be equal to P, okay, delta P delta V, okay, P dV, okay, P dV or P1 V1 and so on. We can just write down like this one for these two states, okay, P1 V1, okay, negative and so on and on. But let me just write down as a change. So change, okay, P change V. This change P change V, okay, can be also considered as dV, okay, and in this case I will just write down here like this one, P dV plus, okay, then delta, okay, this is delta U. What is delta U? Delta U, okay, let me write down here, P dV, D, and here P dV plus, okay, plus mCV delta T. Okay, so if you see this one, P dV delta T. So here change in enthalpy, okay, directly you can just get this one because here you know that there will be no change in volume. So derivative volume is constant, derivative of this guy will be 0 directly. Okay, even if you wrote something like P delta V plus mCV delta T, this one will be 0. Why? Because P V2 minus V1. V2 is equal to V1. Okay, so mCV delta T. So V2 is equal to V1. What do we have to do? This one, V2 is equal to V1, so you get V1 minus V1. Okay, time T plus mCV delta T. So it will be 0. Okay, I will remain only with this mCV delta T. So what will I get? What will I get to this one? So for this one, enthalpy will be equal to mCV delta T only. Okay? Yeah, just this one. Yes, okay, as I was saying. So, okay. And I said, okay, this will be 0. Actually, there is a tiny mistake here. Okay, so here, here in this one, but no props. Here it will be CP. It will be CP. I'll show this one in another. Okay, just consider this one. I forgot a very important point here. Okay, no problem. See, I will write down in here. Okay, nice. So delta H is equal to, okay, P1 V1, sorry, P2 V2 minus P1 V1, okay, minus P1 V1 plus, okay, because delta H, delta H, okay, in the nutshell will be P delta V plus delta U, okay, and this guy will be PV1 or PV2, P2 V2, and so on, P2 V2 minus P1 V1 plus, okay, and here it will be M CV delta T. Well, surely we would just go and say, okay, this V1 is equal to V2, okay, V1 is equal to V2. It should be like we have P1 P2 V2, P2 V2, P1 V1. Even though V2 is equal to V1, but the pressure are different. Okay, I just missed out this very important detail. The pressure is different. V1 is equal to V2, but P1 is different of P2. So here this cannot be zero. Okay, cannot be zero. So then it will be equal to MRT2 minus MRT1. Do you remember about this formula? PV is equal to MRT. Okay, so for this one, P2 V2 will be MRT2. For this one, MRT1. Then plus MCV delta T. We know delta T. Okay, so here I can be written like this one, NR, and here T2 minus T1 plus MCV delta T. Now it's okay. Okay, we cannot say that this one is zero because P2 is different of P1. So when I subtract this value, it will not be zero. Okay, then MRT2 minus T1 is equal to MCV delta T. So we know R. As the same we did, okay? R, we know that R is equal to what? CP minus CV. What is CP? This is the specific heat at constant pressure, and this is specific heat at constant volume, okay? The amount of heat needed to rise temperature at least 1 degree Celsius, okay? Temperature, a substance at least 1 degree Celsius, but at constant pressure. And this is the same definition and so on. Okay, what is CP? CP, this is the amount of heat needed to rise 1 degree Celsius, okay? To rise 1 degree Celsius of a unit of mass of a certain substance. So this one, but at constant pressure. And the same for this one. The amount of heat needed to rise 1 kilogram of mass of 1 kilogram of mass at 1 degree Celsius at 1 degree Celsius of temperature, okay, but at constant volume. This is for this one. So CP and CV, we just substitute this one. This will be mass, and this will be CP minus CV. Then here I will get these two. It is delta T plus MCV delta T. Now see MCP delta T, okay, minus MCV delta T plus MCV delta T. So this and this will be cancelled out, so it will be MCP delta T. This will be change in enthalpy. The same, okay, MCP delta T. Now we are it. Okay, thank you, but forgot about this one. Here we were making a very huge mistake, because see, here pressure is different, so we should just go P1 and P2, P2 V2 and P1 V1, just like that. Okay, this is just to show that we also made mistake if we are not attentive. Okay, there is no one perfect, so we also make mistake, but the most important is that when we realize that we made that mistake, we have to go and change that. Okay, thank you very much.